So this is the Aspire demonstration of client-side code splitting. The basic goal of this protection is to hide algorithms and hide data. Concretely, we want to complicate static and dynamic attacks by complicating the disassembly of certain code fragments and by adding noise to traces collected by instrumentation tools. So this is the principle of how it works. We have the native unprotected binary or library as input. And it contains code chunks that are extracted from the native code and cross-translated to bytecode. The bytecode is then injected into the protected output library by the Diablo link-time rewriter, together with the virtual machine and some glue code to invoke the virtual machine. At runtime, the virtual machine will interpret the bytecode. As the bytecode format is not known to the attacker, he cannot attack that code statically. And of course, the trace of the virtual machine interpreting the bytecode will be much longer than the corresponding original native code fragment. After this overview, let us have a look at the protection in action. Here we see source code of the SafeNet use case, a software license manager, of which we want to protect the fragment. As it is a sensitive fragment, we cannot show it, but you clearly see it marked by source code annotations. Right before the fragment, a memset 0 initializes some data, and then later the data is filled by the code we want to protect. So let's have a look at the unprotected version of the code fragment in IDA Pro. Here we look for that fragment in the symbol information, which we included for demo purposes, but normally symbol information would of course not be present for functions that are not exported. Here is the control flow graph of the function. You see here the memset and the code fragment that needs to be protected by translating it to bytecode. So now we run the Aspire protection compiler toolchain on the program. And when we then look at the input of the cross-translator, we see a description of the native code that Diablo extracted from the original binary. And what the cross-translator then generated from this extracted code is this. In IDA Pro, the protected binary then looks like this. So you can already see that the control flow graph built by IDA is much smaller than in the original binary. The original one looks like this, and the protected version is clearly much smaller. That's because IDA Pro cannot analyze the control flow past the bytecode fragment. We can see that here in the control flow graph. Here we have the memset, followed by the glue code that will invoke the VM, and IDA does not know where the rest of the function is. This results from the control flow indirection through the bytecode and from the fact that the link-time rewriter Diablo performed code layout randomization. So the continuation point, when the virtual machine returns to the native code, is placed somewhere completely else in the binary. Now let's look at the program in action. First I'll copy the binaries onto the developer board and then I will log in. Now I first produce the fingerprint on the board by running a program with the unprotected library. You see the fingerprint being printed. Then when I run the program using the protected library, we see that on top of the fingerprint, the list of executed bytecode opcodes is produced. That is because we linked in a debugging version of the virtual machine interpreter for the purpose of this demo. And so you see that the virtual machine interpreter is actually getting invoked. The Aspire project received funding from the European Union 7th Framework Program under grant agreement number 609734.